Welcome, students. Welcome to our first lecture for this semester or session. Today we are going to look at one section. We're going to look at section 6.1, and the title of the section is Inverse Functions. This section, for the most part, is a review of something that you've probably seen at least twice in an Algebra 2 class or intermediate algebra class, and then again in a pre-calculus setting. And sometimes in a trig setting you see this topic pop up. So you've seen this material before. It's so important, though. It holds together so much of our course material that we want to look at it one more time. Since you have seen this stuff a couple of times before, you can expect this to go a little more quickly, as you might have seen this presented to you in the first couple of times you've seen this. And this is a calculus course, so we're going to see some calculus topics integrated into this section as well. So let's go ahead and get started. I guess real briefly, though, I indicated to you in our orientation video for the course that the course is done asynchronously, so you can view these videos for the course anytime that's convenient for you. I would suggest that you view them before we have our exams. And once you view the material, go ahead and get started with the homework, which is posted on Canvas. And I guess that's it for now. So in terms of overview or review of overview, so let's get started with the section. So I mentioned in our orientation video that this course covers two main areas in calculus. One, or the first area, is integration, either definite or indefinite integrals, and that's what we're going to be spending about a half of our course on. And the second topic is series, and we'll get to that. We'll cross that bridge when we get to it. So our aim is to learn some techniques of integration that you didn't cover in Calculus 1. In my orientation video, again, I indicated that this course, and I used kind of a funny analogy. I used an analogy or a visual aid of Swiss cheese. That your Calc 1 course represents a slice of Swiss cheese in terms of the cheese representing the calculus that's necessary for STEM courses, for engineering or physics students. In this course, we fill in the holes in many of the holes in the Swiss cheese. So what am I talking about with this Swiss cheese business and stuff? So here's our introduction to why we need inverse functions. Suppose we want to find the antiderivative of x squared with respect to x. This should be an automatic to you. This is simply x cubed over 3. We add 1 to the exponent, divide by that new exponent, add a constant of integration, and there you go. So what if we wanted to find an antiderivative of, let's say, x to the negative 2 with respect to x? So we get the same result. We add 1 to the exponent, we get x to the negative 1 over negative 1 plus a constant. We can either leave it like that or write it as negative 1 over x plus a constant. What I'm basically illustrating to you is the main formula that you learned for powers in your first semester calculus. Suppose we want to look at something like the antiderivative of x to the negative 1/2 with respect to x. So this formula, this idea where you find the antiderivative of certain powers, and I very carefully said certain in that sentence. We find the antiderivative of certain powers by adding 1 to the exponent and dividing by that new exponent and add a constant of integration. Negative 1/2 plus 1/2 is 1/2 over 1/2, divide by this new exponent plus a constant. And again, we could write that as 2 times the square root of x plus a constant. The idea is not to simplify right now. It's just to remind you. And here's a hole in the Swiss cheese that I was talking about. Suppose I want the antiderivative of x to the negative 1 with respect to x. We have a problem. We have a big problem. the big problem is we need this antiderivative for the sciences to work, for mathematics of the sciences to work out, for calculus to work out for us. We need this antiderivative. However, and I'll put a question mark here for equals, we can't simply add 1 to the exponent, divide by that new exponent, and add a constant of integration, because we would get x to the 0 over 0 plus a constant. And this is meaningless. This has absolutely no meaning. To divide by 0 is meaningless. Okay, so what is the antiderivative of x to the negative 1? And the strange thing is that antiderivatives of powers, if you look at those first few examples, the antiderivative of power gives you another power. Antiderivative x cubed gives you a multiple of x cubed. The antiderivative of x squared gives you a multiple of x cubed. The antiderivative of x to the negative 2 gives you a multiple of x to the negative 1. So it looks like the antiderivatives of powers, even fraction powers, give you powers again, except for the antiderivative of this very special power. The antiderivative of x to the negative 1 with respect to x is equal to some sort of logarithm. Some sort of logarithm. Now that's a big leap. Logarithm from the antiderivative of power giving you another power. So there's, in fact, this using the same analogy of the Swiss cheese business, there's a very large hole in the mathematics for sciences that you learned in Calc 1. Okay, so if I were to say true or false, for example, whenever I'm going to be indicating an example, I'll write EX, and true or false, the most general antiderivative of x to the n dx is x to the n plus 1 over n plus 1 plus a constant. What would your response be? Well, if I didn't give you the short intro a few seconds ago with the introductory example a few seconds ago, you might say true. This looks like the formula that we learned, and it's false. This is a false statement. In order for the statement to be true, it has to be true for all n, and it's not true for n equals negative 1. It's false. This doesn't work for n equal to negative 1. That's a big problem. Okay, so that's like as I indicated, that's a huge hole in the Swiss cheese of your math that's going to be filled in. Okay, other examples, the antiderivative of secant squared. Let's see if you can remember that. Take a second to see if you can remember that. You'll need to know that. You learned it in Calc 1. Let's see if you remember. Okay, if you said, or if you thought tangent plus a constant, you're correct. The antiderivative of secant squared is tangent. You must know that. Okay, so if you don't know that, review the short list of integrals involving the trig functions that you learned in Calc 1. But let's move on. Okay, so once we have that idea, what is the antiderivative then of tangent? If you were careless about this, you might say secant squared, and that's absolutely false. The derivative of tangent is secant squared. The antiderivative of tangent is not secant squared. The derivative of tangent is secant squared. And the problem is we need this antiderivative, and it's not available in Calculus 1. This is also some sort of a logarithm. Okay, so there's a lot missing from the integration that you learned in Calc 1, and that's an understatement. It turns out that finding derivatives is very simple. Finding derivatives is extremely simple. We have product rules, quotient rules, chain rules. We have all kinds of formulas for finding derivatives. The opposite is true for antiderivatives. And here's a a very sobering statement, and the statement is that it's almost impossible to find antiderivatives. And you're thinking, no, we can find a lot of antiderivatives. No, we can't. The sad fact is that most integration is done in the sciences by approximate integration, because using the fundamental theorem of calculus to find definite integrals, that is, finding integrals by finding antiderivatives, is at best in the sciences, at very, 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 very best in the sciences, is extremely difficult. Okay, at the very best, it's extremely difficult to find an antiderivative. Usually it's impossible. So why are we learning to find antiderivatives? Well, the short story, and that's the only one you need, is that you're going to need to study a lot of physics. And if you're engineers, you'll study a lot of physics and engineering. If you're any other STEM area, STEM major, then you're going to need a lot of mathematics that involves integration. And in those courses, the problems in the text are designed so that the integrals are possible. And so what we're learning this semester are the tools that you're going to need to be learning the science material that requires integration. And then you go off into the real world and get a job, and you integrate by approximation, by using a machine, a computer, to estimate integrals. So we're learning a short list of techniques this semester for finding integrals that are going to allow you to learn basically third and fourth year physics and engineering courses and graduate work. Okay, so let's continue then. So what's the antiderivative? And we looked at this one. I'm repeating it. Antiderivative of x squared. It's x cubed over 3 plus a constant. So what if we interchange the roles of base and exponent here? What if we switch x squared to be 2 to the x? This is an exponential. We're integrating what's called an exponential function. You talked a lot about exponential functions in pre-calc, not in Calc 1, but in pre-calc. And exponential functions are absolutely critical in the sciences, absolutely critical. Example of how critical they are, populations often grow exponentially. Populations of people, populations of animals, populations of viruses, things grow exponentially. So we need antiderivatives. We need derivatives and antiderivatives of exponential functions so we can describe the rates of change and other aspects that calculus give to functions. We need to be able to find derivatives and antiderivatives of exponential functions. Well, this antiderivative involves some sort of, let's say, relationship to logarithms. And logarithms were curiously absent in Calculus 1. Okay. What is the antiderivative of sine? See if you remember that. And the hint is it's not cosine. The derivative of sine is cosine. So what's the antiderivative of sine? I think you'd get it in a few seconds. If not, I'll give it to you. Integral of sine is negative cosine plus a constant. Okay, so what's the most general antiderivative of the inverse sine? Very difficult. This is not some sort of logarithm. We need much work for this. This is never covered in Calc 1. And the integral of inverse sine is not even an inverse trig function. It's not even a trig function. Let's see. That's probably a decent enough intro to why we need this course, or at least half of this course. There are a lot of holes in your integration, a lot of holes in the Swiss cheese that makes up your integration knowledge of at this point. So what we're going to do is we're going to talk about today inverse functions. We're going to look at inverse functions today. Inverse functions. Why are inverse functions important? Right now, you might think, well, it looks like logarithm functions are important, and that's extremely true. I mean, I guess there's no such thing as extremely true. It's either true or false. That is correct. But logarithms happen to be the inverse of exponential functions, and the example I just looked at now, just a few minutes ago, a few seconds ago, is the antiderivative of inverse sine. Inverse sine is an inverse function. So we need to look at inverses again. Why do we need to look at inverses for the third or second or third time? You've already seen them. Well, frankly, many students forget about inverses. They're not an easy topic the first time you looked at them. They're usually presented at the end of a course, and there may be a lot of time that has passed since you've seen inverse. So we're going to look at inverses again. Keep in mind what I said earlier, that this is a calculus course, and this is probably the second or third time at least that you've seen inverses. So the examples and the homework and our work with the inverse is going to be at not the introductory level, and my presentation is not going to be at the introductory level. So this is not meant to be your first exposure to inverse functions. Okay, but I'm going to try to make it thorough. I'm going to try to go way back to the beginning of inverses. So how far back? Well, this far back. What is an inverse function? What is an inverse function? And think about that for a second. What does an inverse function do? The simplest explanation, or the simplest introduction to an inverse, doesn't even involve math. The inverse, all it does is it undoes whatever an operation does. Okay, that's not good enough for us, but that's a real good start. Inverses undo whatever operations do. Well, we deal with functions. Our operations are considered functions. So what does an inverse of a function do? And the easy answer is that it undoes whatever a function does. So here are a couple of real simple, without even bringing up math, too much math, or even too much about functions. What would be the inverse of doubling a number? Keep in mind that inverses cancel out or undo. I'd rather not use cancel out. Undo or reverse whatever a function does. So the inverse of doubling, if you take a number and double it, if you take 10 and double it, you get 20. If you want to undo what that doubling did, you divide 20 by 2 and you get back to 10. So the inverse of doubling is to multiply by 1/2 or to divide by 2. What would the inverse of tripling a number be? Well, yeah, divide by 3. That's the inverse. What would the inverse of adding 5 be? If you thought subtracting 5, you're correct. What would be the inverse of adding 7? Would be subtracting 7. What would be the inverse of subtracting 15? Would be adding 15. So the concept of inverse is extremely simple. So why is it so difficult to algebra students? Well, because there are a couple of details that make inverses a little rough. So here's the first thing that makes the inverses kind of rough. I mentioned that the inverse of doubling a number would be dividing by 2. The inverse of adding 5 would be subtracting 5. Well, what if we can combine those ideas? What would be the inverse of doubling a number and then adding 5? Now think about that for a minute. What would be the inverse of doubling a number and then adding 5? Well, you know that the inverse of doubling is to divide by 2, and the inverse of adding 5 is to subtract 5. So you might think, well, the inverse of doubling a number and adding 5 is to divide by 2 and then subtract 5. Or is it to do the reverse of those operations? Is it to subtract 5 and then divide by 2? So there's the first problem. the idea of an inverse function is very simple. It just cancels out or undoes or reverses the operation of a function. Well, what if your function has more than one operation? In what order do you undo those operations? Right now, you've probably gotten pretty good with some algebra because you got through Calc 1 and Trig, and there's a lot of algebra involved in those courses. So if you thought the inverse of doubling a number and adding 5 is to first subtract 5 and then divide by 2, you're right. But why should it be that? Why shouldn't it be the reverse or the opposite of that, to divide by 2 and then subtract 5? Okay, so there's our first problem: is how do we undo? In what order do we undo the operations of a function? That problem, although it is kind of involved, turns out to be the simpler of the two problems. The more involved problem, and the thing that really makes functions or inverses difficult for students, is the second problem, and it's this: what's the inverse of squaring a number? And if you're thinking square root, you're wrong. Although you might be thinking, no, I think I'm right. If you take 3 and square it, you get 9. If you take the square root of 9, you get back to 3. So taking the square root seems to undo the operation of squaring. But I'm sticking to my guns on this one. What's the inverse of squaring a number? I'm saying there's no such thing. There's no such inverse. And if you're thinking, 3 squared is 9, but if I take the square root of 9, I get back to 3, so square root and squaring seem to be inverses, then I pose this to you: what's negative 3 squared? And obviously, negative 3 times negative 3 is positive 9. Okay, so then take the square root of 9, and what do you get? You don't get negative 3. You don't get back to where you started. So there's the big problem. Not every function has an inverse. And what makes this a really serious problem, and remember, this is a course primarily for engineering and STEM majors, science majors. So I'm going to let you know that the squaring function is extremely important very early in physics. Without the squaring function, we would not be able to figure out when an object lands if we drop it from off a cliff. And that's an extremely important, very early problem in physics, to figure out when something is going to land when you drop it off a cliff. Okay, if this doesn't make sense to you, if you haven't had any courses in physics, don't worry about it. Don't worry at all about it. My point is that we need some sort of inverse for squaring. Otherwise, we have no science. We have no physics. Okay, so let's get around the problem, both of these problems. The first problem is, how do we find an inverse? How do we undo the operations of a function? In what order? The second one is, how do we get around this problem that not every function has an inverse? Okay, so we're going to need to introduce the algebra into this. There's no getting around it. So let's take a look at those first few functions that I talked about: the doubling function, the tripling function, adding 5 function. Let's move forward with some algebra. So let's think about the function that doubles. F of x equals 2x. That function doubles x. So that's the function that doubles whatever your input is. Input, remember, is the value that you put into the function, value from the domain, or x. Using the notation for inverse that we know, the notation for inverse is f with -1 in the superscript. Really, really stern warning: that superscript does not mean the same thing that you might be thinking that it means, and it does not mean 1 over or reciprocal. We'll get more to that in a second. So the inverse of x would be, inverse of doubling would be to divide by 2. So there's your first actual reminder of algebraically what an inverse looks like. If f of x equals 2x, f inverse of x equals x over 2. Okay, and now what was I talking about, that stern warning? I'm going to write that off to the side here. Warning. 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 F inverse is not the same as 1 over f. We reserve that -1 in the superscript. Superscript basically means the location of an exponent, superscript, as opposed to subscript, a sub 1, a sub 2. The superscript in function notation does not mean reciprocal, even though 2 to the -1 equals 1/2. We're using this -1 superscript as an exponent and -1 superscript as inverse to mean very, very, very different things. Okay. What is this? This is all still part of the warning. What is this? This is inverse sine of x. Inverse sine of x. What is this? Sine of x quantity to the -1. This is cosecant. This is 1 over sine of x, and that is the cosecant of x. These are not equal. These are not equal. The inverse sine of x and the cosecant of x are entirely different functions. So my warning that I wanted to be a brief warning turned out to be not so brief, but important, is that when do we know that when we're dealing with inverses versus reciprocals with the -1 exponent or -1 superscript? And the answer is context. If you write f to the -1 where f is a function, it means inverse. If you write x to the -1 where x is a variable, not considering considered as a function, it means 1 over x. Okay. So back to our functions. So the inverse of doubling is to take 1/2. I'm gonna see if I can move this warning over because I've kind of put it in the space where I need here. Let's see if I'm still getting used to this surface, so please bear with me here. Okay, so it's not going to work. Okay, I'll get better with this as the semester goes on. So please bear with me. Let's do this. Oops. Believe me, it's easier to. There it is. Oops. It's easier for me to fix my videos while I'm videotaping. My video froze up in a second. Thanks for your patience. I had to stop the video for a second to remind myself how to do some stuff. So back to our functions and inverses. These are examples, algebraic examples of functions versus inverses. Inverse. Okay. Second function I brought up was the tripling function. F of x equals 3x. The inverse of tripling would be to divide by 3. I also brought up a function adding 5. F of x would be x plus 5. The inverse of adding 5 is to subtract 5. And then I brought up two problems. The problems were, let's see if I can do this in a different color. First problem, it's still pretty close. Blue is doubling a number and then adding 5. And the answer is, well, there's a couple different answers possible. Is it subtracting 5 and then dividing by 2? Or is it dividing by 2, x over 2, and then subtracting 5? And we know, because we've had inverses a couple of times before, that it's subtracting 5 first and then dividing by 2. But why should that be? Why should that be? Okay. The more complicated, and we'll get to that. The answer turns out to be it's not very difficult to figure out how to determine the order in which we undo operations, or how do we construct inverses. The bigger problem is, what if we have a function of squaring? And the problem is that f inverse does not exist. D and E. Okay. Or is it f of inverse of x equals the square root of x? And the unfortunate answer is that it doesn't exist. These are two problems that we need to deal with. Problems. Okay. And in the end, those of you who've had physics know you can figure out when an object hits the ground, so you do have an inverse of some sort of inverse for squaring. So the good news is we're going to be able to construct an inverse for squaring. So let's do that right away. Let's take a look at finding the inverse of, or constructing some sort of inverse for squaring. Okay. So let's take a look. Let's take a detailed look at the squaring function and see how we can get around the problem that it doesn't have an inverse. Although we do need some sort of inverse for the operation of squaring. So what I'm going to do is I'm going to take a very detailed look at the squaring function. So let's take a look at the function, which for us will be the squaring function. And on this side of the screen, we'll look at the inverse. And I'm putting the word inverse in quotes because this function has no inverse. Okay, but we'll figure out what it should be if it did have an inverse, and then hopefully be able to do something with our function so that it isn't a genuine inverse, so it doesn't genuinely have an inverse. So let's go back to the function, and the function is f of x equals x squared. And I want to look at that function carefully. I want to construct a little chart that's going to have input and output. Inputs are x values, outputs are y values, or f of x values. Inputs are numbers from the domain, to remind you. Outputs are numbers in the range. And I'm also going to put point on the graph of the function. And once I do that, I'm going to construct on the other side a corresponding chart for the inverse, or purported inverse quote unquote. So the input, output of the inverse. I guess I should learn how to spell the word output. Input. My undo button is very slow. Output. And let's take a look at the corresponding point on the graph of the inverse. Okay, so in the input, I'm going to choose very specific values for inputs and outputs. So I want to input 0, 1, 2, and -2. Okay, so if I input 0 for x, f of 0 is 0 squared, which is 0. The point on the graph would be 0, 0. No big surprise. Okay, let's move this along. If I input x equals 1, 1 squared is the output, which is 1. 1 is the point on the graph. If I input 2 and square 2, I get 4. F of 2 is 2 squared, which is 4, so the point on the graph would be 2, 4. If I input -2 quantity squared is 4, so the point -2, 4. is on the point of the is a point on the graph. Now let's do the same thing with the inverse function, but for the inputs of the inverse, I'm going to put the outputs of the original function. So the original function had the first output of 0, so that's going to be the input of the inverse. The second output for the function was 1, so that will be the input for the inverse. The third output for the function was 4, so that will be the input for the inverse. I'm switching roles of input and output. The last output was also 4 for the function, so that will be the input for the inverse. Now I'm going to use some arrows to help us out with a nice visualization. So back to the function, if I input 0, I output 0. So if I input 1, I output 1. If I input 2, I output 4. If I input -2, I output 4. Think about it as inputs get turned into outputs. 0 gets turned into 0, 1 gets turned into 1, 2 gets turned into 4 by the function, -2 gets turned into 4. So now reverse those little green arrows for the inverse. The outputs are now the inputs for the function, for the inverse. If that's not real clear, I'm gonna take the outputs for the original function, I'm going to turn them red, and those outputs are now the inputs, also turned red. If my screen won't work, my surface will let me do it. Good, thank you screen, thank you surface. So back to my first statement about what inverses do. The only thing they do is they reverse or undo the operations of a function. So if I input 0, it should be turned back into the original 0 that the function had. If I input 1, 1 should be turned back into 1. Here's where it starts to show up. 4 should get turned back into 2. And 4 should be turned back into -2. Concentrate on the last one. -2 for the function takes -2 and turns it into 4, so the inverse should turn 4 and turn it back into -2. All I've done is reverse the operation of the function. But notice that that amounts algebraically to reversing the x's and y's on the function in the inverse. So the corresponding points on the graph of the inverse would be 0, 0, 1, 1, 4, 2, and 4, -2. Okay, and if it helps, concentrate on the last points. Concentrate on the last points on function and inverse. The function turns -2 into 4. So if x equals -2, y equals 4. So the inverse, now go to the inverse. The inverse should convert 4 back into -2. Okay, so there's a relationship that you memorized. You very likely memorized in algebra when you studied this the first time, is that if you want an inverse, all you got to do is switch x's and y's. The point -2, 4 is on the function, so the point 4, -2 is on the inverse. The function takes -2, turns it into 4. The inverse turns 4 back into -2. Okay, so enough of that. Let's continue on our little investigation here by actually graphing the function and the inverse. So let's do that. I'm going to put a couple of graphs in. This may take a second. It's been a while since I've done this. So here's XY plane for the function. Trying to move it. I have a very, very slow reacting surface today. And let me draw a set of axes for the inverse. That's a little big. For our upcoming lectures, I'm going to maybe eliminate some data. I've got a lot of data from the previous semester in my surface. I think that might be slowing things down. So bear with me. Here we are. Still a little big. Let's move it over here. Okay. Okay. Well. Okay, that'll work. Oops, too far. Worst comes to worst, I'll stop the video and move things. Okay, so let's take a look at the graph of the function versus the quote-unquote inverse. So I'm going to very quickly, we know what the graphs of these things should look like. These are simple functions we've seen before, but the idea is for us to, again, we're trying to construct a way to make a function that doesn't have an inverse, like x squared, have one. You can do something with the function. And more generally, we're trying to figure out what kind of functions have inverses. So let's plot the function. The function goes through the points 0, 0. I think I'll plot those points in red. So 0, 0. The function also goes through the point 1, 1. And put that point in. Function also goes through the point 2, 2, 3, 4. Okay, so you got those 3 points in red. Function goes through the point -2 and 4. -2 and 4. All right. In fact, I want to label those points. This is the point 2, 4, the point 1, 1, the point 0, 0, point -2, 4, and we'll use the technique we learned in algebra, which we don't use in calculus. We'll connect the dots to get the graph of the function. We know what this function looks like. It's a parabola. We know a whole lot more about quadratic functions, but this one is a parabola. Shaky parabola. Too much coffee today. Let's graph what the inverse should look like. Well, to find an inverse, we're interchanging the roles of input and output. So remember, if the function went through 2, 4, the inverse goes through 4, 2. So really all we need to do is switch the x's and y's and connect the dots. Let's do that. We're gonna need x equals 1. We're gonna need y equals 2 and -2. We're gonna need x equals 4. So here are the points. There, if you take the point on the function, the origin 0, 0, reverse the x's and y's, you get 0, 0 again. If you take 1 and 1 and reverse those coordinates, you're still with 1 and 1. 1, 1. If you reverse the coordinates of the point whose coordinates are 2 and 4, you get 4 and 2. So you get 4 and 2. And if you reverse the coordinates of the point with -2 for x and y is 4, you get 4 and -2. And if you connect the dots to construct the graph of the inverse function, which needs to be a function itself, by the way. If you missed what I just said there, don't worry about it. It's coming up soon. So here is what the graph of this thing that we want the inverse to be, and that is a problem. This is not a function. This is not a function. The inverse of a function needs to be a function. And it's not. It doesn't pass the vertical line test. Remember, the vertical line test says if you can pass a vertical line through any point of your graph, it is not a function. Let me be real specific, much more specific about what the problem with this not being a function is. This is saying that if x equals 2 on the original function, y equals 2 squared, or 4. The inverse is saying that the square root of 4, remember the input for the inverse is 4, and the square root of 4 would have to have the value of simultaneously 2 and negative 2. And that's not true. The square root of 4, the principal square root of 4, is not both 2 and negative 2. There are 2 square roots of 4, but the principal square root, the one that comes from inverting or undoing the squaring function, is only 2. And each number has only one square root, principal square root. In terms of that physics example, this would be telling us that if we, and again, if you haven't had physics, or if this, even if you had, and this doesn't make sense as an applied example, this is saying that an object would hit the ground at both 2 seconds and negative 2 seconds after it's released. And objects, when they hit the ground, after you've dropped them from a cliff or an airplane or whatever, they only hit the ground at one time. Okay, so that's a problem. The problem is the inverse of the squaring function would not be a function, and therefore we don't have an inverse for it. So here's the solution, though, to this problem. If we remove from the original function, the squaring function, the function to the left, or part of the function to the left of the y-axis, then the corresponding inverse would be a function. That may not make sense to you right away. So what I'm going to do is show you. Imagine I'm going to highlight the part of the graph of the original function. Let me see if I can do this in a nice thick marker. Here we are. Here's, in sort of a dotted highlight, real thick marker. Here's the branch of the parabola. Take a look at the branch of the original function, the parabola to the left of the y-axis. That point, that branch corresponds to, on the graph of the inverse, the portion of the graph below the x-axis. Now, how do I know that? The reason I know that is, well, take a look at on the graph of the original function, the point negative 2, 4. When I reverse the coordinates of that point on the inverse, I get 4, negative 2. So that's where that point from the original function got transferred, if you will, to using on the inverse. The point on the function negative 2, 4 becomes the point 4, negative 2 on the inverse. So points on the negative, or on the branch of the parabola to the left of the y-axis, get transferred on the inverse to points on the lower portion of the inverse function, of the lower branch, if you will, the branch below the x-axis. So if I remove from the original function, if I remove these points, the negative branch of the parabola, then I will remove from the inverse, or purported inverse, the lower branch. And that would create a function. That would mean that the square root of 4 is 2, and not simultaneously 2 and negative 2. So here's the bottom line. if I let f of x be x squared and remove the left branch of the parabola, the branch of the parabola to the left of the y-axis, then my function will have an inverse. Well, how do I remove a portion of a graph? Well, I do that by removing a portion of the domain of the original function, the x value. So I'm going to remove the negative x-axis from the domain. So if I let f of x equal x squared for x greater than or equal to 0, then my function will be the right-hand branch of the parabola, and then the inverse will not have quotes on it. It'll actually be an inverse. The inverse will be the square root of x and will be the upper branch of the parabola that opens to the right. And that makes perfect sense for us then in terms of having an inverse for squaring. If you want to take this 2 and square it, you'll get 4. So if you take 4 and take the square root of 4, you should get 2. So if that's 4, the output should be square root of 4. And that should equal only 2. Okay? If you let x equal 1, 1 squared is 1. 1 squared is 1. If you take 1 and take the square root of 1, you should get only one value, 1. Okay? So, what's the big point here? The big point here is for some functions we need to change the domain of the function so that the inverse exists. Functions that have inverses have a special name. These kinds of functions are called one-to-one. Okay. Let's back up a little bit. I don't think that was very clear. The original function f of x equals x squared did not have an inverse. And the reasoning was that if it did, if it did have an inverse, its inverse wouldn't be a function. Its purported inverse was not a function. It didn't pass the vertical line test. Now look at that specific green vertical line that I put in. That green line corresponded to x equals 4, y equals 2, and x equals 4, y equals negative 2. Now, that green vertical line, if we transfer it back to the original function, would come from a horizontal line. The horizontal line would intersect the function at the point 2, 4 and negative 2, 4. So the original function was a function. It passes the vertical line test. The original function, not the inverse. It passes the vertical line test, but the original function doesn't pass an additional test. It doesn't pass what's called the horizontal line test. So if a function doesn't pass a horizontal line test, then its inverse, quote unquote, won't pass the vertical line test. However, if I remove from the function, if I physically remove from the function that part of the function, or a part of a function, that makes that function not pass the horizontal line test, then I will be removing the part from the inverse that doesn't make the inverse a function. So one-to-one functions are functions that pass two tests. They pass the vertical line test because they're functions, but they have to pass an additional test. They have to pass a horizontal line test in order to have an inverse. So one-to-one functions are functions which pass both a horizontal and vertical line tests. I have another way to characterize them in a minute, one-to-one functions. But one-to-one functions pass both the vertical line test, and the horizontal line test. An additional test, the horizontal line test. If a function is one-to-one, then and only then will it have an inverse. Okay, so if you have a function that passes both the horizontal and vertical line tests, then the function is one-to-one, and only one-to-one functions have inverses. So why the name one-to-one? Well, one-to-one, the concept of one-to-one, I used to have a good analogy here. A one-to-one relationship between two people. A one-to-one relationship between, a one-on-one or one-to-one relationship between two people. Here's this example may be okay. Suppose we have, and I'm going to write these couples as ordered pairs. We have a guy. Here's a guy, and he has a girlfriend. Put her in address. So there's a couple. This guy has this girlfriend. If this same guy has, how can I draw another girl? Here, another girlfriend. This is not a one-to-one relationship. A one-to-one relationship is when the guy has the girlfriend and the girlfriend has only one guy, the same guy. This guy has two different girlfriends, so this is not a one-to-one relationship. In fact, this would not be a function. Now, so 1x has only one y. That makes a function. So now suppose, let's do this way. This guy has the girlfriend, and let's do this. This other guy, I'll make him a little chunky, has the same girlfriend. This is not a one-to-one relationship because this guy, this girl, same girl, has the same two different boyfriends, whereas in the first relationship, the same guy has two girlfriends. So this is not a one-to-one relationship. In a one-to-one relationship or a one-to-one function, 1x has one y, and 1y has only one x. In the picture above, without removing the left branch of the parabola, the guy, if you will, 2 has the girlfriend 4, but at the same time, this other guy, -2, has the same girlfriend 4. So this is not a one-to-one relationship. If that analogy doesn't make sense for you, you can just remember that in a one-to-one function, 1x has one y, and 1y has only one x. You don't have repeats of either the x or y coordinates in one-to-one functions. One-to-one functions are functions graphically that pass both the horizontal and vertical line tests. So, let's take a look at a specific example to ingrain the concept of one-to-one functions. So, for example, determine whether the following functions are one-to-one. Determine whether the following one-to-one functions. One-to-one functions. Okay, so A. And to do this, a graph is a good idea. Either visually, mentally visualize a graph or physically produce a graph. We're going to be doing a lot of graphing in this course, so this is also a good example for us to review graphing. So let's say the function sine of x. Is sine of x a one-to-one function? And the answer is what? Does it pass the vertical line test? Of course. We wouldn't be able to write f of x. It wouldn't be a function without passing a vertical line test. Does it pass the horizontal line test? The answer is no. It fails the horizontal line test miserably. Now I'm going to throw out a fill in the blanks question. F of x equals sine of x. I'm looking for a short answer here. F of x equals sine of x is not one-to-one. And not because it's not one-to-one because it doesn't pass the horizontal line test, but I'm looking for a different set of words. The sine function is not one-to-one because sine of x is one word. Starts with a P. Can you think of it? The sine of x is not one-to-one because the sine function is what? Very few students answer this question correctly when I pose this in class, and the answer is periodic. Periodic. The sine function is a periodic function, which means that periodically it repeats its y values. The sine function is a periodic function. You must know the graphs of all 6 trig functions, including the sine function. There's no science without the sine function. The sine function has a period of 2 pi. Periodically, the y values repeat themselves. That's what it means for a function to be periodic. So if you draw a horizontal line through the sine function, it fails the horizontal line test miserably. Horizontal lines will pass through the sine function an infinite number of times. And so the answer to this part of the problem is not one-to-one. Not one-to-one. So let me ask you a follow-up question. Or the next question. Is any trig function one-to-one? Any trig function. And the answer should be very easy for you. Trig is very important in calculus. So we're supposed to know a lot of trig. That's going to come up real soon in our course. In Calc 1, trig didn't play a very large role. Well, you might think it did, but it really didn't. In Calc 2, in this course and beyond, trig comes back like a bomb. So, but don't worry about that. We instructors know that it's been a little while, and we review stuff with you. In any case, is any trig function one-to-one? No. They're all periodic. So here's a question for you. All the trig functions are one-to-one. So none of them is all trig functions are not one-to-one. They're all periodic, so they're not one-to-one. What are the periods of the trig functions? This is a good review for you. Real quick off-the-cuff review. The sine function has a period of 2 pi. Every 2 pi, the sine function repeats the same graph, repeats itself. All of the trig functions are periodic. What is the period of each of the trig functions? Let me make it easier for you. All but 2, all the trig functions, all the 6 trig functions except for 2, have a period of what? And those other 2 have a period of what? You get it? If not, I'll help you along. All of the trig functions, 4 of the trig functions have a period of 2 pi. The other 2 have a period of 1 pi. Which are the 2 trig functions that have a period of 1 pi? Did you think of it? Tangent and cotangent. So the only 2 trig functions that don't have a period of 2 pi are tangent, cotangent. So sine, cosine, cosecant, and secant, they have a period of 2 pi. Each of them, of the other ones, the tangent, cotangent, have a period of 1 pi. I mentioned this, but you should know how to graph all 6 trig functions, at least one period of each. Okay. Here's our next example. So part C. F of x equals 2x. The answer should occur to you very, very quickly. What is the graph of y equals 2x? It's a line with a slope of 2. If a line has a steepness of 2, it has to be 1 to 1. What is the only line? Actually, what are the only two kinds of lines that are not 1 to 1? The obvious one is the horizontal line. Any horizontal line fails the horizontal line test miserably. What would the other kind of line be? I think you probably guessed it. If not, vertical lines. Vertical lines and horizontal lines are the only lines that are not 1 to 1. All the rest are 1 to 1. So this f of x equals 2x is 1 to 1. Is 1 to 1. Okay. How about D f of x equals mx plus b? Think about it. What is f of x equals mx plus b? Those are, for different values of n and b, those are equations of lines with a slope of n and a y-intercept of b. So is every line with a slope 1 to 1? And the answer is no. So the answer is not 1 to 1 unless the slope is not equal to 0. So if the slope is not 0, then the line is not horizontal. If the line is not horizontal and the line is a function, that means it's not vertical. It must be 1 to 1. So all functions of the form mx plus b are 1 to 1, provided the slope m is not 0. Okay. Here's another example. This is a course for science majors. So here's a science type question. The question is whether the function is a 1 to 1 function. The temperature of a dead body, a corpse. Let's say the corpse is found in a room whose temperature, not the temperature of the body, the temperature of the room, the room that is 70 degrees Fahrenheit. Does the temperature of a corpse found in a room whose temperature is kept at 70 degrees Fahrenheit, the room's temperature, is that a 1 to 1 function? And the answer is a little more difficult than you might imagine. It depends on our point of view. If we graph temperature, T, let's say for temperature, versus time, and the room is found to be 70 degrees. Let's put 70 degrees here. Then the temperature of the body before it died was 98.6 if approximately. So the temperature of the body was greater than 70. As soon as the body ceased to be alive, as soon as the person died, what happens to their temperature? It begins to fall. And there's an important mathematical model for it, for the temperature, and it's called Newton's law of cooling. And that model says that the temperature will asymptotically approach the temperature of the room. Okay? So, in fact, it's an exponential, it's a certain type of exponential function. So just looking at the graph of this exponential function, the answer should be is 1-to-1. So from a theoretical point of view, let's do this, point of view, the answer is 1-to-1, 2-1. And the temperature of the room asymptotically approaches 70, but never quite reaches it. The theoretical model provides that. The real-life model says to the contrary. The real-life model, we know that if we put an object in a room whose temperature is 70 degrees, the object's going to cool down to be 70 degrees eventually. So the real-life answer would be no, the temperature of the body will eventually hit and stay at 70 degrees Fahrenheit. So here we get an inkling of some of the problems with the mathematics of the physics and of the sciences versus real life data. The mathematics of physics only estimates what's going on, or approximates what's going on in the real world. So if I pose this question to you, or if this question were posed to you, you would have to ask a follow-up question as well. Are we looking at theoretically, is the theoretical temperature of the corpse or of the body a 1-to-1 function, or are we talking about real data, real life data? Okay, so if this were a theoretical model, it would be a 1-to-1 function, and so it would have. This function would have an inverse. Okay, don't concern yourself with questions like this popping up on tests and stuff. I'm not going to make you differentiate between whether we're talking about a real life example or a theoretical model and so forth. So, okay, so let's take a look at. Some properties of inverses, reviewing some properties of inverses, including how to answer or address the simpler problem is how do we find the inverse? How do we undo the operations of inverses? Right now we know that only functions that are 1-to-1 have inverses. Now I want to review with you properties of inverses. Further properties of inverses. Inverses. Again, this is not meant to be a first exposure to these properties. You're supposed to have seen these. So if these aren't familiar to you at all, then you're in the wrong place. I don't think that's going to be the case. I don't think you would have gotten to Calc 2 without having Calc 1 and Pre-Calc. So I think you're safe. So, first property. If f of x equals y, then what is f inverse of y? Oops, f inverse of, now that does not look very good. So let me erase that. Let me redraw that. So that's better. So if f of x equals y, then f inverse y equals what? This should be very clear. If it's not, it should equal x. Think about it this way. The original statement, f of x equals y, means the function turns x into y. So the inverse should turn y back into what? X. Functions and inverses the only thing they do is they undo the operations of each other. This is a very fancy way of saying that if the sine of pi over 6 is 1/2, then the inverse sine of 1/2 should equal pi over 6. So there's nothing really sneaky going on here with this statement. Okay, let's take a look at the next property. What is the inverse of the function of x? What's the composition of f inverse with f? This is little more than a statement of the thing we just said above. Think about the inside parentheses. The function turns x into something. F turns x into something. That's f of x. The inverse turns that back to what? X. Functions and inverses cancel each other out. And it doesn't matter how you compose them. So f of f inverse of x equals x. Okay. What's that important for? Well, this is how you can tell that you have an inverse and your inverse is correct. We know that if the function is the doubling function, then the inverse is to divide by 2. So how can you verify that? Well, verify that by showing that these two statements, that f inverse of f of x equals f and that f of f inverse of x equals x, that they cancel each other out. Okay, so f of, I'll do one of them, f of f inverse of x is f of, well, what's f inverse of x? It's x over 2. But what does the function do to x over 2? The function takes whatever you put into it and doubles it. So 2 times x over 2 equals x. So f of f inverse of x equals x. If the other, and I might as well do it, if the other equation also holds true, that is f inverse of f of x equals x, then your inverse is an inverse. Then your function and inverse pair are actually inverse function and inverse. So what's f inverse of f of x? It's f inverse of f of x equals 2x. And what does f inverse do? It takes whatever you put into it and takes half of it. Well, we're now inputting 2x. So f inverse of 2x is 2x over 2. And that's back to x. So we have both of those equations holding true. Function and inverse cancel each other out. The graphs of function and inverse. Okay. F of x, f, and f inverse are always symmetric. Metric about y equals x. Always, always, always. Well, what about f of x equals x squared? Well, that wouldn't have an inverse, so we wouldn't have that necessarily true. What about f of x equals x squared for x greater than or equal to 0? That function has an inverse. It's the square root function. We spent about 15-20 minutes talking about it. Graph both on the same set of axes. F of x equals x squared. F of x equals inverse, f of x equals inverse of x equals square root of x. F of x equals x squared. F inverse of x equals the square root of x. Those two graphs are symmetric. They are reflections of each other across the line y equals x. This is always true. This is always true. Okay? And now let's answer let's solve the first problem, not the one of inverses existing. That is, how do we find an inverse? How do we determine the order in which we undo the operations of a function? So finding f inverse of x. Easy. You can reverse these steps, by the way. They don't have to be done in this order. Switch x and y. That should be pretty clear. If you want an inverse, you switch x and y. Remember, if a function turns 2 into 4, then the inverse turns 4 back into positive 2. So switch x and y is the first step. And the second step is to solve that new equation for y. Solve for y. Okay, let's take a look at a couple of examples. We're almost done here. Let's say, for example, okay, find f inverse of x. We'll do one tough one, one easy one, and one tough one. Find f inverse of x. A. Let's go back to the original, first of the few original problems. Doubling a number and adding 5. The big question was, Do we find the inverse by subtracting 5 and then dividing by 2, or do we divide by 2 first and then subtract 5? So let's not have to worry. We don't have to worry about it. Let's not worry about it. Let's use the process for finding the inverse to determine the answer. 1, switch x and y. Well, we can't switch x and y if there's no y to switch. So remember, f of x is another fancy way of saying y. So now switch x and y. So x equals 2y plus 5. Step 2, solve for y. Subtract 5 from both sides, isolate y. And divide both sides by 2. And when you've solved for y, you have found the inverse. So the inverse is first subtract 5 and then divide by 2. Okay. Now I'm going to end this lecture with a problem that is much more of the level of difficulty that you will be expected to deal with. This is a calculus class, and this is your second or third time around with inverses. So it's expected that you're able to use calculus or use your thinking in calculus to solve more complicated problems. So here is our more complicated problem. Suppose I have y equals, or f of x equals 1 minus the square root of x plus 3. And I want to find the inverse of this function. Okay. Well, if we proceed as in the last part of this example, switch x and y and solve for y, we almost get there. Okay, so let's do this. Let's introduce y. Let's switch x and y. And now let's solve for y. This isn't too bad. Let's take the square root to one side. We can do this. Minus square root of y plus 3 equals x minus 1. Okay, so really I just took the 1 to the other side, to the left-hand side, and then reverse things. And square both sides. Y plus 3 equals x minus 1 squared. And subtract 3 from both sides. And you might be thinking, Professor Leon, this isn't that bad. Well, it's also not the correct answer. So switch x and y, and then 2, solve for y. This can't possibly be the answer. Think about it for a second. This can't possibly be the answer. What is the graph of this thing that we're calling the inverse, this x minus 1 squared minus 3? It's a parabola, and parabolas are not one-to-one. This can't possibly be an inverse, because the function and the inverse, in order to be function inverse pairs, they have both got to be one-to-one. This can't be one-to-one. This is impossible. Impossible. It's not 1, sorry about my writing here, to 1. Not 1 to 1. Okay, so we have a little more work to do. In order to find the inverse, we need to do something with that last equation. We need to restrict it so that it is 1 to 1. Well, how do we restrict it? Well, it's a parabola. We take off half the branch. Well, which branch? Well, we can't just arbitrarily take off the left branch of a parabola. And what if it's the right branch that inverts this function? Okay, or the left branch that inverts this function. Okay, so the easiest way to do this is to graph the original function, I think, to graph the original function, and then use the graph of the original function to determine what part of that parabola is the actual inverse. Okay, so let's do that. Let's graph the original function. The original function is y equals 1 minus the square root of x plus 3. Okay, you should be able to come up with a graph of this in about a minute, a real accurate graph of this in about a minute. Now, the fact is, I know a lot of students have forgotten how to do that. So I'll remind you, in pre-calc, you can do this with pre-calc. In pre-calc, we teach you how to graph. In fact, pre-calc is mostly about graphing. It's mostly about memorizing basic shapes and then using transformations, shift to the left, shift to the right, shift up, shift down, stretch by factors, reflections, and doing that to what's called a library of functions, library of parent functions, like common functions, x squared, x cubed, square root of x. So this is nothing more than a transformation, a set of transformations of the square root function. So what you notice is that this represents a certain transformations of the square root function. What does plus 3 do to the square root function? It shifts which way by how much? And the answer, it shifts to the left by 3. Okay, what does the 1 represent? It represents a shift up by 1. The original function, if to see that, you could have written the square root first, and then the 1 later. So adding 1 to the function shifts it up by 1. Replacing x with x plus 3 shifts to left by 3. What does the negative coefficient of the square root do? And the answer is, if you remember, it's a reflection across the x-axis. Reflection in the x-axis. So we'll do this very quickly, step by step. You have the square root function, which we memorize. Absolutely got to memorize it. If we reflect it across the x-axis, we get negative square root of x. Y equals negative square root of x. If we shift that function to left by 3, we get 1, 2, 3. So this would be y equals negative square root x plus 3. If we add 1 to that, we shift the function up by 1. 1, 2, 3, 1. So the end result then looks like y equals negative square root of x plus 3 plus 1. This is the graph of the original function. The inverse needs to be a reflection of this graph across the line y equals x. So I'm going to draw that in green. Now the original function goes through the point negative 3, 1. So the inverse should go through what point? Switch them. 1, negative 3, negative 1, negative 2, negative 3. So the original function goes through the point 1, negative 3. Now the function and the inverse need to be reflections across the line y equals x. So here's the line y equals x in blue. Now, the inverse, the function that we'd like to be the inverse, remember that has to look like y equals, let's see, let me back that up a second. The inverse needs to be y equals x minus 1 quantity squared, the parabola, minus 3. What does that look like? and I'm not going to go through all the transformations. I'm going to do it very quickly. It's a parabola with a vertex at 1, -3. Well, there's its vertex graphed in green. It opens up. So if I were to graph it, it's going to look like this. It's going to open up. Okay, so there's the graph of this purported inverse. That can't be, again, that can't be an inverse because it's not 1-to-1. So one of those branches goes away. Which one is it? If I erase the left branch of that parabola, I'm not going to get a symmetry about the line y equals x. So if I eliminate the right branch of that parabola, I'm going to attempt to do this with my eraser here. Okay, small eraser. If I eliminate the right branch of that parabola, see it going away? Then what I'm left with is, my graphs are sometimes a little funky, but this looks like it should be symmetric about the line y equals x. I am producing a graph that's symmetric about the line y equals x. Okay, so in order for this function, the green function, to be the inverse, I need to restrict the domain of the inverse to be x less than 1, less than or equal to 1. That will get me the left branch of my parabola, and I will have an inverse. So f inverse of x equals x minus 1 squared minus 3, but only for x less than or equal to 1. Okay, so that's the end of our first lecture. Feel free to access the homework on Canvas for section 6.1, and I will soon post a video for section 6.2 for tomorrow, and I'm looking forward to talking with you again soon. Thanks.